The principal component analysis is a widely used tool for data science applications, right. It is also called the KL transform. So, given the data samples, I would like to figure out the eigendirections in the data space using an objective function that minimizes in some sense the energy over that maximizes the energy over the first k components in my eigenspace, right. So, I can set up this problem. So, the principal component analysis basically begins by looking at the data samples, forming a covariance matrix from the data samples, figuring out the eigen decomposition, and then arriving at the eigenvalues and the eigenvectors in the data space, so that any vector in this space can be expressed in terms of the eigenbasis, and depending upon the energy constraints that I have, I can discard certain components or certain components in the eigenspace, and I can retain only those that I require, and I have a more compact representation now, and that forms the basis of the PCA. I mean in terms of the salient ideas. And a discussion of the derivation of the PCA algorithm is done in my lectures in the mathematical methods and techniques for signal processing course. So, the interested reader can go through these lectures, particularly lectures 75, 76, 77 etc. in the videos in the mathematical methods and techniques for signal processing course. In this lecture, we will sort of extend on the PCA, given that we have dealt with kernels in lieu of Mercer's theorem, and we know that we can go from the input space to a feature space through a nonlinear transformation, and we do the KL expansion or the PCA in the feature space. So, it is a small extension, but it has some interesting consequences, and we will discuss this derivation, and that leads us to the kernel PCA algorithm, because we are invoking the kernel here and doing the PCA in the transformed space. Okay. So, let us see how this works. Most forms of PCA involve computations in the input space or the data space, right, whichever way I want to call this. Now, we can also do a PCA in the feature space, which is nonlinearly related to the input space. Now, if you recall this diagram, I have points xi in the input space. So, xi belonging to R, say M, from here through a nonlinear transformation I go to the feature space, and this is phi of xi, and this belongs to say some space Rn where n is greater than m, and I do a PCA in the feature space. Okay. And we have to be mindful that in the feature space we deal with these inner product kernels, and therefore we have these as a consequence of Mercer's theorem, right. So, let us set up some details here. Let phi be this transformation from R m naught to R m1. So, I am changing my notations here, maybe I can make this consistent. I instead of m I make this m naught and n I make this m1. Okay. So, that settles this on the last slide. So, phi is this transformation which is non-linear, and denotes phi of xj basically denotes the image of this vector xj induced in the feature space by the nonlinear map phi. Okay, this is a basic this is a basic definition of the image of the point induced in the feature space. Now, what are we given? We are given the points xi, I equals 1 to capital N, and we can compute phi of phi of xi, we compute phi of xi over all these points. Accordingly, we can define a correlation matrix in the feature space, right. So, we can compute a correlation matrix using the outer products of the images of these vectors in the feature space. And this can be done as R tilde equals 1 upon n summation I equals 1 to capital N phi of xi times phi of xi transposed. Now, we assume that the bias is 0 in the feature space. If not, we can compute the bias and remove this bias from the data points. So, as with the ordinary PCA, ensure that the bias 1 upon capital N summation 1 to capital N all the vectors in this feature space, this is 0, that is the mean in the feature space is 0, that is we remove the bias. So, I have to compute my correlation matrix in the feature space. So, what I have to do is basically set the bias to 0, and if the bias is not 0, I compute the bias, I take the feature vectors, I remove that, I subtract that bias, and on that I compute the correlation matrix. So, once this is set up, like the way we did, we can formulate an optimization problem. I will not discuss the details of the optimization problem because that is dealt with in the video slides in the mathematical methods and techniques for signal processing course. So, we can proceed and compute the eigenvalues and eigenvectors over the correlation matrix by solving this eigenvalue equation. R tilde q tilde is lambda tilde q tilde, where lambda tilde is the eigenvalue of R tilde and q tilde is the corresponding eigenvector of R tilde. Now, for an eigenvalue which is non-zero, for lambda tilde which is not equal to 0, satisfying this eigenvalue equation, I call this equation 1. There exists a corresponding set of coefficients alpha j, j equals 1 to capital N, so that I can express q tilde as a linear combination of my elements in the feature space. Now, I plug q tilde in this eigenvalue equation. So, I plug 2 in 1, I plug 2 in 1 here. So, what I get is as follows. So, for R q tilde, I will end up with this equation summation I equals 1 to n, summation j equals 1 to n, alpha j phi of xi times the kernel acting on xi xj equals n times lambda tilde times summation j equals 1 to capital N alpha j phi of xj, right. So, what I have done is pretty straightforward. I expand this this matrix R tilde using this equation here. So, maybe I can call this equation A, right. So, I use this equation A and equation 2 in 1, and I can simplify this in this form. Now here this kernel is straightforward. This kernel K of xi xj is defined as phi transposed xi times phi of xj, right. And because of this outer product, I had this phi transpose that I got from my R tilde, and I have that plugged in along with what I have for Q tilde, and then I simplify in this form. This is pretty straightforward algebra here. Okay. So let me call this to be my equation 1, right. In capital 1, I have not used this notation before, I have not used this symbol before. Now multiply, I would say pre-multiply this equation 1 both sides by phi transposed xk. So you can clearly see when I do a phi transpose xk on this kernel is basically this is basically a scalar because it is an inner product. Now I have phi of xi times phi of phi transpose xk, and that I can realize using my kernel definition, right. So I can simplify this as summation I equals 1 to n summation j equals 1 to n alpha j. So I have phi of xi times phi transpose xk, and I call this kernel xk with xi times this kernel xi with xj, and I have in the right hand side of equation 1, when I multiply by phi transpose xk, I get n times lambda tilde n times lambda tilde summation j equals 1 to n alpha j. So this phi of xj times phi transpose xk will give me this kernel xk, kernel acting on xk and xi. Okay, this is sort of xj here, right, xk and xj. Yeah, I missed the j here. I put the j, I put the I instead of j, so we make it xk and xj. Okay, this is consistent. Now this kernel matrix can be computed for all possible pairs of points xi xj, where I and j go from 1 to n. So by computing the kernel matrix or the gram matrix, I can pull the elements that I need in this computation, and the n by 1 vector alpha is this, has a jth element which is alpha j, right, and I can figure out the alpha j from my alpha vector by graphing out the jth coefficient. So this is sort of straightforward. So there are some interesting points here. K square times alpha, if I write this messy equation that I have here involving summations etc. in the form of a compact matrix equation, I can write this as k square times alpha equals n times lambda times k times alpha. So, I rewrite. So, this is, I call this equation 2. I rewrite equation 2 in matrix form, right. So, just a small note that this matrix K is my Gram matrix comprising of the kernel evaluated over the pairs of data points xi and xj, right. Ij goes from 1 to n, and alpha is my vector. If I want, I can put this vector here, which is my column vector stacked by alpha 1 to alpha capital N. Now, simplifying this, right, because I can, assuming that my Gram matrix inverse exists. So, I pre-multiply by k inverse on both sides. So, I can simplify this as k times alpha equals n times lambda tilde times alpha. So, this is my simplified eigenvalue equation that is realized in terms of the kernel matrix or the Gram matrix capital K and the data samples, the number of data samples which is capital N. So, the rest is, so alpha is my like my eigen vector, and lambda tilde are my eigenvalues of my Gram matrix or the kernel matrix capital K, right. So, let lambda 1 lambda 2 in this order let this denote the eigenvalues of the kernel matrix K. Okay. Now, if I set lambda j to be capital N times lambda j tilde for j equals 1 through n. So, you can see this equation here, right. If I set it like this, where lambda j tilde, this is the jth eigenvalue of the correlation matrix R tilde, right. Then I can, setting up like this, then I can write this equation, the simplified eigenvalue equation, which is k alpha equals n lambda tilde times alpha as k alpha equals lambda alpha, where lambda is the eigenvalue which is given by n times lambda tilde, right. So, this is pretty straightforward. So, what I did was the following. So, I just had k square alpha equals n lambda tilde times k alpha. So, I just replace lambda j to be n times I define lambda j to be n times lambda j tilde, and then I plug this in. I have a more simplified way in which I can represent. So, k times alpha is basically lambda times alpha, where lambda is defined as capital N times lambda tilde, right. So, your lambda here is n times lambda tilde. So, I have removed the subscript here because corresponding to the eigenvector alpha j, you have a corresponding eigenvalue lambda j. Now, there are some more details here. The vector alpha needs to be normalized because it is an eigenvector, and this requires. So, I will write the vector alpha is to be normalized, and this requires that the eigenvector q tilde of the correlation matrix R tilde to be normalized to unity, right. Which means q tilde k times q tilde k transpose times q tilde k equals 1 for all k equals 1 through p, right, 1 through n. So, if you are arranging the eigenvalues in decreasing order, then you can formulate like this. And also you can verify that from these results alpha k tilde, alpha k is this vector, alpha k tilde times alpha k transposed times alpha k equals 1 upon lambda k. You can verify that alpha k transposed alpha k is 1 upon lambda k. This is, I would leave this as an exercise, and this verification you can do from this normality condition that you want to bring in for this vector q tilde k. So, this sort of completes the details that we require for the kernel PCA algorithm. Let us try to summarize what is really happening here, right. So, conceptually I have, let us say, imagine points are in a 2-dimensional space. I have these points So, I just have a set of points x in this 2-dimensional space, and these are non-linearly mapped into points in the feature space, right. I may have this is a 2-dimensional space and this is a 3-dimensional space, and I can form my eigenbasis. I put phi E in this space. So, I form the eigenbasis in this space. I call them E1, E2, E3, and I can represent the points in this space, right. So, for which, given the training samples, I need to compute the kernel matrix, and then from the kernel matrix I need to solve an eigenvalue problem. So, the geometry is sort of what we have here. So, I have x1 and x2 in the feature in 2-dimensional space. I have x1 and x2. Let us say I have a nonlinear transformation that takes me from a 2-dimensional space to a 3-dimensional space, and in the 3-dimensional space I do this eigen decomposition and I have my representation in this form. Right. So, here are the steps that we need. This is like the algorithm for the kernel PCA. So, given training samples xi I equals 1 to n, compute the n by n kernel matrix or the gram matrix given by k equals k xi xj, where this element k xi xj is phi transpose xi times phi of xj. The next step is solve the eigenvalue problem, which is k times alpha equals lambda times alpha, where lambda is the eigenvalue of the kernel matrix and alpha is the corresponding eigenvector. Then normalize the eigenvectors. Is alpha k transposed alpha k is 1 upon lambda k. Now, you can arrange the eigenvalues in the descending order and stack the eigenvectors in the corresponding directions in the corresponding way. You can arrange the eigenvalues in the descending order and stack the eigenvectors linked to these eigenvalues. For extraction of the principal components, of a test vector x, basically you need to take the projections of phi of x with respect to the eigenvectors, right. This is basically the inner product of the eigenvector with the vector in the feature space, right, and this is how you can compute the projections and then from this you can represent the vector in the feature space and look into corresponding compact representation if you want in the feature space, right. So, this completes the details, but you may question what is the need for kernel PCA and what it actually does, right. For example, in the data space or in the input space, depending upon my measurements, my coordinates have a physical meaning, right. For example, first coordinate is a pressure, second coordinate is a temperature, third coordinate is a distance, etc., etc. By formulating the correlation matrix in the input space, I can have a visualization as to what is happening over correlations across these coordinates, etc., when I do the PCA. But in the feature space, since I am doing a nonlinear mapping, right, the nonlinear mapping helps me to go to higher dimension where the geometry of the data points is in a different in a different space. So, you may question, what do I need, why do I need to go to a higher dimensional feature space and then do the PCA. So, this can be in applications that demand so, right, because the PCA is a linear transformation in some sense. So, when you have the points in the input space, you are thinking about of having a linear transformation that compacts the energy in some space, basically because it is like a data compression problem, right. I do the eigen decomposition and I am basically representing using a linear transformation only those coefficients that I really want to retain and throw away those components that I do not want. But there may be applications for better realization or better visualization of the geometry of the data points where I can go to higher dimensions, and that is where I may want a feature space. And this may be also required in pattern recognition applications. For example, I have an input signal, maybe a raw image or a raw speech signal, from which I need to extract the feature vectors, and the feature vectors can be extracted through linear transforms or possibly through nonlinear transforms, depending upon what I really require in my applications. And in that space where I need feature vectors that are really important for me in my applications, I may need a PCA to further compact the energy in the feature space or components in the feature space. So, and that may be the reason where the kernel PCA algorithm may find applications. But if you directly think, when I go to the nonlinear space and I do the PCA, I lose my physical representation as what I had in the original space. That question may come into your mind, because I am doing nonlinear transformation, and what is meaning of the coordinates in the feature space? They may not mean anything, it may be abstract. But in that space, if I want to do dimensionality reduction by optimizing or compacting the energy through linear transformation, then I will need the kernel PCA algorithm. Okay. So, that summarizes the necessary details of the algorithm and the applications towards motivating the kernel PCA. So, the derivation of the kernel PCA in terms of optimization problem can be done straightforwardly, like what I did in the derivation of the ordinary PCA. So, you can look into those videos and basically set up the same framework here. If not, we will do this as part of the homework exercise.